Good afternoon, ladies and gentlemen. I'm going to talk about work on finding socially tenuous group for online social networks. I'm Shen from National Tsinghua University, Taiwan. So, we all know much about socially dense groups in online social networks. For example, cliques, K-cores, plex, clans, K-choose, N-cliques, quasi-cliques, and F-groups. We know all of them. And indeed, this kind of socially dense groups inspire many applications, such as activity organization, or socialization event planning, or the expert information problems. However, socially tenuous groups have not received much research attention. Here we say socially tenuous groups, we refer to the subgraphs that have very few or even non-interactions or relationships. Here's an example. Assume we have a social network, and if we're trying to extract 4 vertices out of it, then V1, V2, V6, and V8, they have no direct friendship, and they do not even have friend-of-friend relationships. So this is these 4 vertices form a socially tenuous group because they have very few interactions. We might wonder, what are the application scenarios for such socially tenuous groups? So we are going to talk about some of them. The first one is about therapy group for mental disorders. As we all know that group therapy is one of the most effective strategy for mental disorders, where the major functionality of therapy groups is that we allow the patients in the group to share their feelings and allow the other patients to provide social support and their help. However, there is one very important criterion. That is, members do not know each other, or they sometimes do not even be multi-hub friends. This is because if the patients, they know each other, or they have some interactions with each other, when they are sharing their feelings, they might be afraid that the secrets or the feelings may be spread out, and they may hesitate sharing those information, and the therapy group collapse. So in this scenario, the social tenuous group finding these kind of groups can help finding effective therapy groups. So let's take a look at an example. Assume that we are going to find 4 patients from a social network. Assume that we have preprocessed the social network that to include only the patients with similar symptoms and they are suffering from the same disorders. So for the first group here, V3, V4, V5, and V8. Actually, this is a socially dense group. And in fact, this is not good. So for the second one, we have V2, V4, V7, V8. This is a little bit better because they do not induce any ages. However, it is not good enough because there are still common friends. Although these V3 and V5, they are not selected in the group, but they can still act as some bridges to link those patients and provide some degree of interactions. Finally, this one, V1, V2, V6, and V8, it seems to be the best choice because there's no direct friendship and it minimizes the friend-of-friend relationship. And indeed, this is an effective therapy group and a socially tenuous group. Another application scenario may be more, we are more familiar with this reviewer selection. That is, in addition to expertise and the research areas a reviewer has, we're also trying to find reviewers who are not socially close to each other in order not to let them influence each other's opinions to ensure unbiased assessments. So in this case, socially tenuous groups can help us find the reviewers for papers. So after this very high-level concept of social tenuous groups and motivating examples, now we turn our attention on how to model the tenuity of the groups. One alternative approach is to find groups of vertices that induce no age at all. In fact, this is the traditional independent set problem. However, this is not effective to capture the idea of tenuity. This example again, we can find, although V1, V2, V4, and V8, they form an independent set. However, they still have common friends, and they might have interactions to some degree. So this is not a good choice. Therefore, we propose a new notion called K-triangles for measuring tenuity. A K-triangle is a set of 3 vertices such that the shortest path distance measured in halves between any 2 of the UVW vertices does not exceed K. So here are some examples. For this one, this is a 1 triangle, V2, V3, V5, and this is the conventional triangle. And for these 3 vertices, V3, V4, and V6, indeed, it is a 2 triangle because V3, the shortest path distance from V3 to V6 is 2, so this is a 2 triangle. Finally, this is a V1, V3, V5, this is a 3 triangle because the distance from V1 to V5 is 3. Please note that the shortest path can pass through some vertices not selected in the K triangle. So this is a 3 triangle. And we might ask another question. Why are we using triangles to measure tenuity? Our answer is that triangles serve well as basic unit to measure various density relationships, such as clustering coefficient, transitivity ratio, or K-truths. In fact, the fewer the K-triangles are in the group, the more tenuous the group is. Again, this example. This socially dense group, it has 2 1 triangles and 4 2 triangles. This slightly better one, it has 0 1 triangles and 4 2 triangles. And finally, this one, we said this is the best one. It has 0 1 triangles and 0 2 triangles. So we believe that K triangle will capture the idea of tenuity. In fact, there are many good properties of K triangles. For example, a K-1 triangle is also a K triangle. And if a group has no K triangle, it has no K-1 triangle, has no K-2, and this relationship repeats recursively down to 1 triangle. So if we can minimize the number of K triangle in the group, then we are indeed minimizing the other K-1, K-2 triangles. So after the definition of K triangles, now we can detail our problem formulation in our paper. We propose a problem of minima K triangle disconnected group, or called as MkTG, where we are given a social network and 2 parameters, N and K. We are looking for a subgraph F from G such that the average number of K triangles in F is minimized, where the average number of K triangles is calculated as the number of K triangles in F divided by number of vertices in F. Moreover, to make this problem more practical and reasonable, we add 2 constraints. The first one is the size constraint, where we require the selected group to be at least n vertices. Because if we don't have this, because we don't want to find very small group with only 1 or 2 members inside. The second one is the no pair constraint. This is more obvious because we don't want to find individuals who induce ages in the original social network. So with the objective function and these 2 constraints, this problem is very challenging. In fact, we prove in our paper, it is NP hard and inapproximable with any factor. So this means that unless P equals NP, we cannot find the polynomial-time algorithm to solve it. So before we detail our algorithm, we first take a look at the naive approach. The idea is that we are trying to find socially dense groups on the complement graph. And then we hope that a socially dense graph on the complement graph can map back to the original graph to form a socially tenuous group. However, this approach does not work This is an example. This is a complete graph we constructed. And the 5 vertices here, they have density exactly 1. That is, they have 5 vertices and 5 edges. However, these 5 vertices, when we go back to the original graph, we find there is 1, 2 triangle. And indeed, this subgroup violates the no pair constraint. So this naive approach does not work. So to address this, we propose an algorithm called TERA that try to tackle important factors of MkTG. The idea is that we try to include isolated vertices, we try to remove the vertices appearing in many K triangles, and we try to generate multiple candidate groups to choose the best solution from. So specifically, at the very beginning, we assign each vertex V with a weight WV, where WV is the number of K triangles V is involved in. Then our algorithm iteratively removes a vertex V with a maximum WV to form a candidate solution, and we output the candidate solution which is feasible while including the minimum objective value. So here's an example. The input graph is here, and it can be regarded as the first candidate solution. Then we remove V5, which has the largest WV. So here we got the second candidate solution. And then we remove V2 and then V4. So now we got 4 candidate solutions. The algorithm stops here because it doesn't have to consider any candidate solution with fewer than 3 vertices. And finally, we extract the candidate solution with a minimum objective value where it satisfies the no pair constraint, and which is this one. Okay, so the TERA algorithm, it works effectively. It can find good solutions. However, we still find that there is room for improvement. So this is because in the original graph, there are some redundant vertices that we don't even have to scan over them. So this motivates us to provide some advanced processing strategy, or we call TERA-ADV, that include 2 important pruning strategies. The first one is called simplicial pruning, and the second one is called vicinal partition and elimination. These 2 strategies, they work differently. However, they both are based on the main idea, the equivalence of vertices. So indeed, in every instance of the MkTG problem, we found that some vertices, they contribute equally to the objective value and constraint. So we group them together, and we found that only one out of each group, only one vertex can be in a feasible solution due to the no pair constraint. So we simply keep one and prune the others. More specifically, in a simplicial pruning strategy, given the graph and the vertex, we define that the 1/2 neighbor of x as n of x, and the closed neighbor of x to be the 1/2 neighbor x plus x. So a simplicial vertex S is a vertex where its 1/2 neighbors form a clique. So given a simplicial vertex, we can prove that at most one vertex in its closed neighbors would appear in any feasible solution. So we can simply keep S and trim the others, that is, their 1/2 neighbors. So this is an example, V1, V2, and V10. Each of them is a simplicial vertex. And for example, V2, its neighbors, 1/2 neighbors are V3 and V4, which form a complete graph. So for simplicial pruning, we simply trim off V3 and V4 and leave only V2. So actually, the simplicial pruning strategy is very effective. It can trim off a lot of vertices to reduce the computation overhead. For the other pruning strategy, vicinal preorder and elimination, although it works differently, but it uses the same idea. So due to a time constraint, I cannot go into details of it, but if you're interested, please refer to our paper. So we perform extensive extensive experiments on 5 different real datasets with vertices ranging from 45,000 to 1.6 million. We first show some experiment results on different datasets. Here we use Instagram, Facebook, DBOP, and POCAC. We would like to know the correlation between the K for K triangle and the objective value. So as we can see, as K increases, the objective value increases. This is because more vertices in F, the solution, are within the K hubs on G. More importantly, IG incurs the largest objective value. This is because IG is the densest among those real data sets. We also compare our approaches with other relative ones. So for BF, this is a brute force algorithm that tries to enumerate all combinations to find the optimal solution. So since it's a brute force, it does not scale up, so we have no choice but to sample a small subset of IG. Otherwise, BF does not return in reasonable time. PMC is an algorithm, existing algorithm to find maxima clicks on complement graph. RND is to randomly select n vertices from the original graph. And BC is another community detection algorithm on complement graphs. So this is another approach to find socially dense subgraphs in a complement graph. The result shows that the PMC and BC, which are two representative algorithms for finding socially dense groups on complement graphs, they perform poorly because they do not even consider anything about K triangles. For us, our proposed TERA-ADV algorithm, which can obtain very high quality solutions, which are very close to the optimal solution, the lower ones here. Finally, we compare the feasibility ratio of the different approaches. Here, the feasibility ratio is the ratio of solutions that satisfy all the constraints. And our algorithm, TERA and TERA-ADV, achieve very high feasibility ratio, where RND, the random one, performs poorly because it does not consider anything about no pair constraint. There's one thing that worth noting, that the PMC algorithm achieves quite high feasibility ratio. But the PMC algorithm is not a good algorithm because if we roll back to see here, PMC achieves very bad objective values. So PMC is not a good approach. So in this paper, we believe this is the first work that extracts social tenuous subgroups from social networks. And we propose a new notion of K triangles. We propose two algorithms, TERA and TERA-ADV, to solve the MkTG problem. And the algorithms outperform baselines in terms of computation time and solution quality. So thank you, and any questions?